Thanks for coming. My name is Boshan. I work at Subsplash as a release engineer. And I've coming from a Ruby background. And then 2 years ago, I'm using Elixir. And then now I'm using Erlang. And when I'm learning Elixir, I'm reading a lot of books. And most of the books, when it tells about the recursion, they will say that the tail-recursion optimization. And also from some books, it's saying you should use the tail-recursive optimization because it will keep the stack the same, so you will never running out of the stack. And I somehow get this feeling that the tail-recursive functions are much faster than the body-recursive functions. So maybe you guys have heard of this. So today's talk is to talk about why this is a myth and how can we understand more about that. So first of all, Erlang is a dynamic typing system. Let's just imagine if given us a task, let's just implement a dynamic system for Erlang. So there's only one require, which is this language is a dynamic typing system. So for the information on the memory, so information consists of the bits and the context. For example, here is a piece of memories. So it has 8 bytes here, and then it stores some binaries in each byte. And then if it's for static typed languages, so if it's a 1 byte char type in C, so the compiler will know that okay, I'm gonna reading each byte as 1 byte. So this is just hello. And then if it's 2 bytes for the short type, it's going to be a different value like for the integers. And if the compiler telling is just 4 bytes means 1 integer, so it will become integers. So as you can see, all the bytes here stays the same. It's depending on how the compilers it's telling the programmers to understand it. So as for a static typed language, you don't need to put the types information inside of the data itself, right? This is the Erlang's building block. That's assuming that this is all the Erlang's types that we want to implement. And as you can see, we have the integers, float, atoms, tuple, list, maps, and binaries. So in here, we got 7 types. So the most naive implementation would be, okay, now we have 7 types, right? So we can use 3 bits to represent this 3 type. Because 2 to 3 is 8. So here we can just use 3 least significant bits just to put it in the right-hand side. And then for each type, we'll just give them 3 bits. So that you can see we can use 7 bits here to represent all the types that we want. And then we have 1 is not being used, so we just reserve it. And as you can see, this system, it will work. However, it's not very scalable and convenient because later, if we want to add more types, then this part is not so easy to add more. So in Erlang, the type system is being implemented similarly, but a little bit advanced. So this is the C code on the Erlang's virtual machine. So it's pretty much 1 line of code to define the type of the Erlang's term, so which is unsigned long. So unsigned long is just basically telling computers, I'm gonna use 1 word size for any Erlang term. And then from the 34 bits machine, so that's going to be 4 bytes, and then 64 bits are going to be 8 bytes. Okay, so in here we have there's something called data alignment property. For example, here is a very simple C code. We have an integer and give a value of 100, and then print the pointer of that integer. And assuming we are running it 4 times. And then, as you can see, each time this blue part is a returned address. And then if we put that into the binary, and we'll see that and then look for the 2 least significant bits on the right-hand side. So the yellow part would always be 0. So this is a data alignment property for the CPU's optimization, so that we can at least use those 2 bits for free, because every time we initiate something, we allocate something, it's always have this 2 0 bits. Okay, so for Erlang, it's using a system called a staged tag scheme system. For example, this is a list, and because we already have 2 bits for free, right? So we can just use this 2 bits, and then Erlang has a lot of lists, so we just use 0, 1 for list, and 1, 0 for boxed value, and 0, 0 for the header. We'll talk to that later. And then now we have only 1, 1 left, right? So when we have the 1, 1, and then we'll call it an immediate type, we'll just look for another 2 bits before that. And immediate type means the term is small that can fit into one word size. So that's why it's called immediate type. So we have reading 2 more bits, like 0, 0 gonna be PID, and 0, 1 is port, and 1, 1 is small integer. And now we have 1, 0 left, right? But we still have more types. So what Erlang does is, for the 1, 0, it's gonna be another stage, like intermediate 2. So in here, we're gonna read 2 more bits here. So we have 0, 0 for Adam, 0, 1 for catch, and then a last 1, 1 for nil. So that is like how it's a staged part. So with this mechanism, we can use the bits to their maximum efficiency. We good here? Okay. And here is a box header. So when you have the immediate type, it's just to feed everything into one word size. But if it's for a larger thing like a tuple, so you need to have multiple bytes for that thing. So you need to know which type it is. So you need to look for the header information. So the header starts with 0, 0, and then looking for 4 more bits here. And then here are all the types for that 4 bits. As you can see, the tuple is here, and then we got 2 types of integers. And for the binary, we have like binary match context, refc, heap, sub-binary. So on the internal representation of the Erlang binary, they have like 4 types. And also we have the maps here, and this one is not used. Maybe later we can add more things. I'm not going to everything because it's boring. So I'm just gonna show a few examples. For example, for the small integers here, the small integers will start with 1, 1, 1, 1. Okay. So as you can see on the 32 bits machine, we got 1, 1, 1, 1 reserved. So all the X part means all the actual data part. You can just put your actual number on those parts, so that the limitation on here is easy to understand. For example, on the 32 bits, and with all so 32 bits minus 4 will be 28 bits, and then we reserve the first bit for the sign, so we got 27 bits left. So which gives us the range for the 2 to a 27 minus 1 for the largest positive integer, and then the minus 2 to a 27 to the lowest one, and then same on the 64 bits machine. So this is like the range for the immediate small integer, okay? And for the immediate 2, we're gonna look at the atoms. So the atoms will starting with 0, 0, 1, 0, 1, 1. And so it's the same idea for the small integer. So all the x are the actual part we can put into. So for the atom, there's no need for the sign or not sign. It's just like C's enum type is pretty much an integer. So the maximum on 32 bits will just everything is 1. And then, but however, on the 64, due to some implementation detail, it's not using all the bits here. So for the default, if you don't do anything and start an Erlang shell, it will use 20 bits, which is give you 1,000,000 atoms. The minimum is this number 8192. So when you start an Erlang shell, it will create a bunch of predefined atoms like true, false, OK, arrow. And then, in fact, if you change, when you start an Elixir shell with this little number, it will crash right away because Elixir will create more atoms for the system to be running. But as you can see here, is here explaining the reason why you cannot have so many atoms in one beam system, because that's how many ones you can put in this one word size. Okay, another one is a nil. So if you look closely, the nil is actually starting with all ones. So the end part, the last few one is 0 or 1 1 0 1, 1 1 0 1 1 0 1 1, and then it's just all the ones in the beginning, regardless it's 32 or 64 bits. So this is exactly what nil type is represented in the memory. So it's always look like this. There's few things to say that this nil is just an empty list. This empty list is the actual nil type, and it's not the nil in Elixir. The nil in Elixir is just an atom. It belongs to some atom tables. In here, maybe you would ask, why does it need a nil type? Because if you think of Erlang, is the data structure for the Erlang is a list, and then for the list we have the header and the tail, and then for the last one we will just point into a nil type, which is this empty list. Okay, so on the primary tag part, now let's checking. So previously we checking the immediate type. Now what about the part that need more than one word size to fit in? We'll look at the list first. So the list starts with 0 1. If you're programming with Lisp, so it's the same concept. A list is just a const cell with a char and cater, and then you just put a cater on the left and char on the left and cater on the right. And here is a very simple list with just one and 1 here. So the char part, it will just actually put the 1, and then the cater part is just the empty list, which is a nil type. And this is a data part, and this is a memory, and this is actual data. As you can see, 1F just 1 1 1 1 1, which is the immediate type, and then here is the nil type. So the nil type will always look like that. And what if we put another element in the list? As you can see, we can check on the second part. For the 1 and this list, this const cell, the actual data is 1, and then the next pointing to another term. And then if we look closely on the representation on here, so it's 201. And as you can see, every list starts with 0 1. So 201 means, so you just minus out 1. So the actual memory address is 200, which you look in the 200 here. And then in here is the next list const cell. So it has the data of the 2, and then it has the nil type in the end. So if it's an empty list, it's just this nil type, which is an immediate type. Okay, now for the boxed value, the box value will start with 1 0, and then the next memory, the next word in memory will be the header starting with 0 0. So it will read 4 more bits to know which it's the actual type. We'll just look at the tuple here. So the tuple, we got 2 for 0 0 for the headers, and then 4 zeros for the tuple type, and then this is a empty tuple. As you can see, the empty tuple, the internal representation on the empty tuple is just all zeros in the memory, because it's this zeros means first means what is the type, and then it will tell you how many more word size I need to look. In this case, there's no more, so that's 0. If I have 1 here, so it will just put, okay, I have 1 more, and then the runtime will just looking for 1 more word size, and then which is actually store the 1 here as a immediate type. Same with 2, it will just looking 2 more word size. Okay, now that's enough of the background for the Erlang's dynamic system. Now let's walk through this myth that tail-recursive functions are much faster than body-recursive functions. For example, let's write a very, very simple Erlang program, and one is using, all it does is just +1 on the list. And one is a tail-recursive version, and which we use a accumulator as a helper, and then in the end, we need to reverse it. And another is a body-recursive function, which is nice and clean, like that. Okay, now let's see what is the memories looks like when we run these two versions. Let's run with the tail-recursive first. So here it's the process. When we start the process, it's just a few KB of memories in the few KBs allocated memories in your memory. And then a process will consist of a stack and a heap, register, and mailboxes. And then the heap and stack, they are like this same piece of memory. And then if you put something on the stack will grow. And you put something in the heap will grow like this. And then it will just, when you run stuff, it will just do like this. And then what happens when the stack meets the heap? A garbage collection will be triggered. And then it will just remove all the unnecessary stuff. So let's see the tail-recursive functions. Now we provide 1, 2, 3, 4, 5. It will be first put in the stack, and then here it's our the one here is our header, and then the empty list is our accumulator, and then the 2, 3, 4, 5 is our tail. And as we running it, and it will just we +1, and then we put the result back to the heap, like 2 in the heap, and then our accumulator now is a 2. So if you look closer, maybe it's too small. The number here for the accumulator is the memory address is AC13C9. And then if you -1, so will be AC13C8. So which is if you look into the heap, that's where it's actually located. So it will see, okay, it's located here, and then which is just a 2. Okay, and then we just keep going it until we got everything, until our tail becomes empty. And now we need to run our reverse part, right? And then on the reverse part, the Erlang's list reverse is implemented in C. It will just reverse right on the heap. So that's all my functions, like 6, 5, 4, 3, 2, and after I'm reversed, I got 2, 3, 4, 5, 6. And then after that, the stack will return with a valid result that's stored here, but here is actually not referred by anything. So when next time the garbage collection kicked, and this part will just be gone. Okay, now let's see the body-recursive function. The body-recursive function, there's no accumulator. So when I got my first element 1, and then I'm plussing with 1, which is 2, and then because I'm entering another function without returning first, so I need to put that 2 into the stack, which looks like that. It will just put the 2 in the stack. And then keep going, we'll put a 3, 4, 5, until the last one, 6. And once we got here, and then we will return an empty list. We are not calling ourselves. So then it will just pop all the stuff we put in the stack back onto the heap. And then it will look like this. And then our stack will be empty. And then all the actual stuff is put on the heap. Okay, so as you can see, if we are going back and just watch this very quickly. So for the tail-recursive version, when we are doing that, it copies stuff directly on the heap. And then, as you can see, that the stack stays the same. So stack never grows. And then in the last, when they do the reverse, it will copy everything back to the heap. It will just do directly on the heap. And then on the body-recursive part, it's the its heap stays the same, but the stack keep growing. So and then in the last, it will copy everything in the heap. So as you can see, even in the body recursive functions, it doesn't have those unlinked memories. So it even look cleaner. Yes, but for the so let's look at the code here. For the computer, one is growing in heap and one is growing stack. So for the computer, it's the same kind of memory. So it actually doesn't matter too much. But for the programmer's perspective, the the tail-recursive, we need accumulator, so we need another function here. But for the body-recursive, it's just 2 lines. It's easier to write. So the conclusion on the dismiss, so this is the same word on the Erlang's efficiency guide. So maybe it says, use a version that make your code cleaner. It's usually the body-recursive version. And also, it says a tail-recursive function that does not need to reverse a list at the end is faster than the body-recursive function, which also makes sense because if we need to reverse the list in the end, and that reverse part will take a lot of time. But if we don't need to reverse, or if we don't even need to build a list, we just, for example, adding something up, we'll definitely just use the tail-recursive function, so that the stack and the heap will all stay the same. Actually, when we look at the implementation on the list map function, it's just a very plain, simple body-recursive function. Here are all the resources. It has the white papers on explaining the staged Erlang type, and also there are a few books that are written about this part. And then the best source, of course, is the Erlang source code. That's it for the talk. Thank you. At Subsplash, we're using Elixir, and we also use Golang. And it's a Seattle-based company, and we are hiring now. You can talk to me if you're interested. That's it. Thank you. Any questions? Yes.
Does the length and size of the list you're dealing with matter? Because when you garbage collect off the heap, if you've got a consistent stack, you garbage collect right off the heap. But if you do the other way around, the stack can grow, has to be maintained the whole time. So does the size matter?
So the question is, when the garbage collection started, does the size matter for if you put everything in the stack? So this is a very good question. And so when the stack meets a heap, when they meet each other, and the garbage collector will making the stuff on the heap on the stack, or whatever on the stack referring on the heap, they will making that put into a new piece of the memory, and then it will remove all the old one. And then if the list is very long, it will grow the process size, like by 2, and then it will just put enough of the things here, and then it will set some high water bar stuff. But I haven't really looked into the source code how the garbage collector works, but the size won't really matter. It will just being garbage collected. Yes, doing a larger allocation for the piece of memory.
You mentioned that there's a little over 8,000 default atoms.
Yes.
Is there a lot of garbage that's not used, or it seems pretty high?
The question is when we started the Erlang's shell, it will start a few thousand atoms. So what are those atoms? So those are atoms like the true, false, okay, and and with a lot of kernel modules. Because every time we use a module, it's actually an atom, and the atom is never garbage collected. It's just a table that inserting one thing. and then the internal representation for the atom is just an integer, a number. It's just for the programmers to know which of this. So it will start in a lot of things, but yeah, those are the atoms needed when we start the Beam instance.
Why Elixir using much more atoms than Erlang shell?
The question is why Elixir is using much more atoms than the Erlang shell. I've actually tried that. Remember, the nil type is Elixir thing. I think they will add the stuff like the nil type, and also the Elixir module. When we start a Elixir IX, and then it will start the application of Elixir. And application of Elixir, it has all the enum, stream modules. So all these modules will take it's actually considered as the atoms. So it will add a lot of elixir.enum, elixir.stream, and then to the table. So it's about 10,000. So that's why when you use like 8,000 minimum, and you start, it will crash right away. And then if you look to the crash dump, it will say that it's just that you're running out of index of the atom.
More questions? All right, thank you, Boshan.
Thank you.